record. I think there was an audio bug in the last recording, and I figured it out. For some reason, it just got rid of all my audio devices on the recording software. Not really sure why, but it seems to be working now. So that's fixed. Other administrative notes. The second assignment extended one last time to tomorrow night, so one more day on that. So just please turn it in by tomorrow night if you can. I think that's about it. Assignment 3 is also up. If you want to take a look at that, it's also due next week. It's a little over a week before it's due, in between this one and the next one. Anyways, I guess we'll get started with the actual class stuff. So first things first, I wanted to just do a little bit of a review on the pointers that we talked about last time, partially because the audio was cut out, but also just because I think it's a little bit of a difficult topic, and we're also going to keep talking about it today. So recall that we had a memory space. My pen is on the wrong screen. Let me fix that. Now my pen should totally go. Oh, there it is. Okay, cool. Sorry. A little confused for a second there. But we were talking about memory last time, right? And that kind of stuff. And so we said that there's always like a straight line that I can't draw very well. And this represents where all of our stuff, our programs, all of our variables, pretty much anything we use in a computer is going to get stored here as long as it's running. And we said that there were these things called addresses that basically just served as a way to mark where is this thing stored. You might say something like this. And then whenever we create a variable, so if I was to go into my C++ program and write int x, let's just say equals 3 so that it's initialized, then what the compiler does is it knows something about these addresses, or like what address space it has, and it goes to some random space and allocates an integer, or whatever variable type. And in this case, we said an integer was 4 bytes, so it just marks the top of it and then how big it is. So we'll just put x there. That's where x is. This is all x. In fact, maybe rather than an arrow, I'll do it this way. And then we said we had really like two kinds of operators for these things. So we had the ampersand and then the star. Does anybody, just as a refresher, know what this would print in our example? Right? Yep, I'm seeing in the chat the address of x, or hex01, which is the address in our example, right? So this would print hex01, which is the address of x. Right? And so that's the address is always the starting point. So notice that x takes up 0, 1, 0, 2, 0, 3, and 0, 4, but right, we always just mark it by whatever the top is. So the ampersand was like the address operator. It gets the address of the thing. And then we said the way that we could make a pointer is we put the star in front of it. I could make something like a pointer, and then we could store the address that we just mentioned like this. And then what would something like this print then in this example if I put a star in front of the pointer? Does anybody remember what the star operator does? Let me get rid of this end line so that we have a little more. Right, and then somebody in chat says the value of x, which is right. So this will print the value of x, which is 3 from that first line. Cool. That's a good job, you guys are right. So, just a refresher, the ampersand operator gets the address of something. A pointer is a new kind of data type that just represents a address holding variable that holds addresses of that specific data type, although really it technically can hold the address of anything, and then you can kind of change what data type it's looking at. And then the star operator just dereferences it. It's called the dereference operator. So it only works on pointers, and it goes to that pointer and interprets the data at that location, so whatever the value is. And then we said, it's based off of whatever the type is of that thing. So since this is an integer pointer, it goes first to that address, which is the pointer there, and then it says, well, an integer, that's 4 bytes, and then it interprets the 4 bytes that are there, which in this case is the bytes that make up X, so that's totally fine. But if we change the type of this or try to cast a pointer, remember we said that we might run into issues because there might be different interpretations of different data types, or they might be different sizes, and so we might just go into data that we don't want or something like that. So that's just kind of like a general review of what we did last class, and we were doing some things at the very end, and we ran out of time. I know there was an example we were doing that was going to give us like a new thing called a memory leak that I wanted to talk about. That was this. So I actually added like a bunch of comments and stuff since last class, just because I uploaded this to Canvas and I wanted everybody to be able to get something more comprehensive. So rewrite in main, we had this class called an example that was basically just like 1 or 2 members. It was kind of just a random class we made, and so we ended up allocating a new variable of this example class. So we have an example pointer here, and we made a new thing. So remember, the new keyword was something we went over at the very end, and it just constructs an object similar to what we're used to with the normal constructor, except it returns it as a pointer instead of just as a object. So this creates a new example and then stores it a pointer to that object. And then we said we were going to call this function makeExample that we wrote that did value reference. So we talked a little bit about passing by value reference, and then it overwrites that pointer, and then it goes away. And so there's something that we actually have to consider with this pointer stuff, and it has to do with memory management. So C++ doesn't actually do a whole lot of memory management for you, which makes it a little bit hard for beginners, but it actually is more efficient when you have the ability to do this on your own to some extent. And so that's why C++ does it. So it has more potential in it, but a lot of other languages will manage this stuff for you. And so just as a kind of walkthrough as to something like that, let's say I'm going to write, instead of a function call that we wrote last time, I'm just going to write this all as like one big code block. So let's say I make some sort of class. So we'll just say we have that example class again. I'm just going to pretend it has a default constructor. I don't remember if it does. But let's just say that we make a new example. And so in memory, that's just going to go somewhere. We don't care about these addresses, and it's just going to allocate however many spaces an example takes, and there's E. So E is here. It's a pointer in this case, so I think I'll just do an arrow for it. That's where that is. And then I have the ability to just reuse variables, right? So right now I have this E takes up this space. Maybe I should do it with a different color than red. Let's just say it's like that. And then I might have, a bunch more memory, because probably have a few gigabytes. And then I might go and redefine E to point at some new object. So let's say I go and I'm like, okay, well, I'm done with whatever I've done with E. I wrote some code that does this stuff, and then I decide, okay, I need to make a new example, and I'm just going to reuse this variable so I don't take up any extra space or make new variables or anything like that. And so anytime we do a new, it just allocates the space. So let's say it goes down here, allocates new space, and then we get a pointer to this space right here, and E is now going to point to that instead. Right, and so we lose this pointer, but the way C++ works, you don't actually get rid of any of this stuff. So all of the stuff that made up this first part this yellow part right here, that is still there, and all this stuff that made up this new one is the stuff that we're currently pointing to. Now, we need some way to get rid of this, otherwise we've kind of lost it. So one thing to consider here is that this pointer is no longer pointing to this yellow space where E used to be, which means we have no way to get back to it, and the compiler or the runtime environment doesn't keep track of where these things are that we've lost control of. And so when this happens, it's called a memory leak. And it's when you just have memory that is no longer reachable, but is still in use. Whenever you go to allocate memory by creating a variable or any other kind of allocation, then the runtime, or more than likely the operating system, will only give you memory that is not currently allocated to something else. So even though we're no longer using that old E space, that yellow part, it's still registered as being allocated, so the system still thinks it's in use, and we have really no way to get back to it to tell it's not in use anymore. So we've effectively just lost all of this space and we can no longer use it anymore, which is not very good. It means that we might run out of memory later, or we might have to ask for more memory from the operating system than we actually need, which is going to slow down our program a little bit because it needs to take the time to ask the operating system for more memory, and might slow down other programs. And if you were to open Task Manager on Windows, you would see it's just consuming way too much memory, and we want to avoid this. So before you ever transfer any sort of pointer, what you should do is what's called just delete. I'm going to try and move this down a little bit. So to avoid a memory leak, let's just move that line down there. Erase the old one. Then what we need to do is delete the space that you used to point to before we overwrite the pointer at all. So if you're ever going to overwrite the pointer, make sure you delete the stuff that used to be there, unless you're doing something really complicated where you have multiple things that point to this. But if you ever think it's going to be the last thing that's pointing to it, then you definitely need to make sure to delete. So there's a keyword in C++, it's just called delete, and it always takes a pointer. So delete E, which is a pointer, and what this will do, if we go back to what we had before, by this line we had E pointing to the first yellow area. Now if we delete it, it's going to deallocate all of this. So it says, okay, this is free, and now it's usable. And then after that, we go and point to here. So we no longer have that memory leak problem. We've told the system that it's allowed to use the memory there again, and everything is good and fine. Case in point, just make sure you are deleting everything that you do. There's a equivalent to this. Sometimes they ask it on tests, but I'm never going to ask you to write it in a program. It's called free. It's the C equivalent. So almost everything in the language C is supported by C++, so you can also use the word free and then put the variable, and that should do the same thing as well, but that's C related, so I'm going to say don't do that. And I see a question, what is a destructor? I'm about to get to that, so thank you. You are on the right track. It actually has to do with this, so let's actually talk about that now, because I think that's about everything for this. Whenever you delete an object, it's going to have a thing called a destructor. So whereas a constructor was something that's called on creation of an object, a destructor is something that's called automatically on the deletion of an object. Now that can happen either via the delete command. So here when I delete E, the example deconstructor is going to get called, but you can also have it happen when a variable gets deleted just naturally. So for instance, if I was to go off here on the side and I just wrote a function called void foo, and it took an example, let's just call it E2, and then it does whatever, and then the function ends here, then all of the locals stop existing right here. Any parameters, in this case just e2 and whatever we made down here, get deleted at the end of this function. In that case, they're going to call their destructor, and a destructor, whereas a constructor handles initialization, a destructor will delete anything that needs to be deleted when that thing disappears. So first things first, let's go over how to write a destructor, and then we'll talk about when you would actually want to use a destructor. In this example, a destructor is not going to be practical because of the variables that I'm using here, but I'll write out an example in a second where it would make sense. Anyways, the way that you declare a destructor is using the tilde, and there's only one kind of destructor per class, and it's always the default destructor. A destructor cannot take any parameters, it's always blank. And the reason being is because we either just are deleting it straight up, or we are having it go out of scope. And neither of those things are things that you really control too much the way that they're actually being called. And so it doesn't really make sense to add parameters to it. So if I had like E0 here, it's going to die at this line because that's the end of main. So we have main here. E0 is declared in main, and it dies in main as well. And that will end up calling the destructor. Now, the destructor here, I can't really do anything, but I can at least maybe put C out. The destructor was called. I don't think I have all of these names set up, do I? Some of these don't have initialization, so I'm not going to print out anything else, but we'll just run it here and we should see that it prints that destructor stuff. Again, these are really just special types of functions that are called on creation and deletion, and so they don't really necessarily need too much special going on, so you can do really anything in them that you want. As we see, it gets called 4 times. Presumably I made 4 variables. That seems to be the case, so it's going to call it on E0, E1, E2, 3, and 4. One of them is not getting called, and I'm not entirely sure why. But you notice it actually doesn't get called on pointers. The pointers actually don't get deleted unless you specifically use the delete keyword, which actually means that I do kind of have a memory leak. When the program ends, it just forfeits all of its memory anyways, but if you run some kind of memory profiler that shows you what memory was not properly deallocated in your program, these 2 pointers are actually going to be an issue because I'd never used the delete keyword on them. For the sake of the example, let's throw one down here. I don't know why it's only doing 4 and not 5. I'm not sure which one of these is the issue. Maybe it's E1, I'm not sure. But just to rerun this, we'll see that it should print it 5 times this time, or 1 more time at least. The destructor was called 1, 2, 3, 4, and then we have an extra one. So we had 4 last time, we have 5 this time, and that's because the destructor was now called for the pointer. So just consider if you go out of scope, the pointer doesn't actually get deleted. The pointer itself gets deleted, but the object that the pointer is pointing to doesn't get deleted. So also if you're creating new pointers within a function, you should also use the delete keyword there if you want to avoid memory leaks. In main, it's not really a big deal in practice because that's the end of the program anyways, and your memory's just going to get forfeited over back to the OS regardless. But it's considered good practice, and I would say be aware of it because I see some people write assignments where they ask you to do that, and it's kind of important to consider the memory. So just make sure if you ever declare a pointer that you're deleting it before the end of the program. For good practice, let's also delete ePointer2, and now everything's deleted except for one of these, which I'm not sure which one it is. But that's okay. This does get initialized. We can actually check, I guess. Let's see, the destructor was called for... Let's just throw the name here. We had like a string for a name. I'm actually curious. Not all of these are names, so it's probably not going to be the most helpful. We see it was called for goodbye, world, hello. Oh, one of these is probably getting called for this one. No, that's not right. It's getting called for goodbye. Accidentally clicked on something that I didn't mean to click on. There we go. Goodbye, world, hello. Goodbye would be this one. World. Another world. Which I assume is that one. I overwrite E pointer 2 at some point. Oh well, let's not get caught up on it. Some of these are getting deconstructed. I apparently have like some sort of bug somewhere. Any questions on destructors so far? Regardless. Okay. I think two more things that I wanted to talk about with regards to pointers. The first one was just a C++ thing. You actually see that I did it here. Normally you write things with a dot operator, right, when you want to access members. So if I had E3 here, I had a function called print members that belonged to that class. So I could do something like E3.printMembers, and then it'll just go and print the stuff. The equivalent to that, if you're using a pointer, is to use this arrow. It effectively means exactly the same thing. A lot of other languages will drop it entirely and just use a dot every single time, which I think is nice because really they just all do the same thing. But C++ makes some sort of distinction here where if you want to access the members of a pointer object, or a pointer to an object, then you have to use the little arrow instead. So that's why you'll see in my example code I have these. It's effectively the same thing as this, it's just the way C++ does pointers. So we have questions. So if you call delete on a pointer that points to an object that doesn't explicitly have a destructor, only the pointer will get deleted, but if the destructor is explicitly written, the pointer and the object will get deleted. So the object gets deleted if you haven't explicitly written one. The compiler will actually fill it in, much like it fills in a default constructor if you don't write one, because it needs to have a constructor in order for the class to exist. It'll just write a constructor that does nothing. If you don't write a destructor, it will just automatically generate one for you, and it will generate one that does nothing. Which is fine in this example, actually, that we were doing here. Let me move that up. Because of the fact that there's nothing that I really need to delete. The string and the int will actually delete themselves in the destructor, so I don't actually need to write anything. I wrote the C out here, but it would be fine if I just left it, because that was kind of a trivial piece of code that I wrote. You only ever need a destructor if your object has pointers itself. In that case, you need to delete all of the pointers that the object has, which, thank you for reminding me, I did want to mention that. So we didn't need it for that example class that I wrote, but if I had, let's just say, ex2 as a class, and this kept a pointer to the original example class, pointer, we'll just call this E, and then maybe I write a constructor ex2, and then we'll just say it makes E equals a new example, and that's all it does. I should write a destructor for this one because this class contains a pointer in it. Whenever you delete an object, it is considered going out of scope for all of the variable members that it contains. So if they're not pointers, it will just automatically deallocate them the way it would. But if you keep a pointer to something, because something else could be pointing to it, it doesn't deallocate it, because I could very well have somehow obtained this E pointer in some other class and still need it for some reason, just depending on your application. So it just keeps it live. if you ever have a pointer, then it's suggested to delete it. So in this case, I would say the destructor here would delete E, whatever that points to. Whenever I create a new ex2 object, let's say I go later in code and then write this, ex2, and create a new object, then it will allocate this whole thing. This is where ex2 is, and then, you know, it fills in all that stuff. And then because it has a member in it that is a pointer to something else, it'll have an E member, and that will point to another object that could be somewhere else in memory. So this points to some kind of, let's just say, E object that exists. And that being said, whenever you delete this object, because it has a pointer in it of itself, you need it to delete any of the things that it points to. So this destructor here will first delete that space, and then it will delete this from wherever the deconstructor was called. So simple answer is just, if your class contains a pointer, you almost always want to write a destructor that deallocates all of those pointers. Otherwise, you're okay. Just get away with it. Or something else I was going to mention about this, and now I'm spacing out on it. I remember like halfway through talking through this. Two things actually. So one was just make sure if you've already deallocated something that you don't accidentally re-deallocate it or do anything after that point. If I wrote this line of code, which does the stuff that we showed in that messy diagram up there, then I can't try to do something like this. A, because it's restricted and this is going to be inaccessible, right? But pretending that that wasn't an issue. This is bad. This is a no-go. You're going to get a memory error from this. And the reason being is it's already deleted. All this stuff is gone. Probably not realistically, like the bytes are still probably there, all the bits and ones and zeros are probably still there, but as far as the system is concerned, you're not using it anymore when you type delete, and something else could have overwritten it, who knows. In that case, you're not allowed to access anything of a variable that has been deleted. If you do that, you're going to get some kind of bad read access violation probably, because you're trying to access data that's no longer yours. It doesn't belong to you anymore. It's the operating system's now. In much the same way, there actually is a special type of pointer that I haven't talked about yet, and that is called a null pointer. And let me make a pointer to this first off. That's the way that should look. If I wanted to just not set it to an object, then I have the ability to set it to a thing called null. And it's all caps in C++, and just actually represents the number 0. You'll see if you look at it in the debugger, it'll just be 0 and then a bunch of zeros after that. And this is just used as a way to tell that the pointer is not currently pointing to anywhere. So if I actually did this here, it doesn't automatically allocate any space, which is actually kind of nice. You can delay when you do the allocation. If you don't make a object variable a pointer, it just automatically goes and allocates all that space right away as soon as you do it, which can be kind of bad for performance because that takes time to do, to actually allocate all that space. So you can delay it if you just maybe think you're not going to do it, or you think there's a better time to allocate that space when you can kind of hide the fact that you're allocating stuff. But if you just make a pointer object, it doesn't actually go and do all this allocation that I showed earlier. It just makes a pointer, and most compilers will just have it point to garbage. And so try not to also access anything before you've set the pointer either, because that also means it's not pointing anywhere. As a safety measure, it's a good idea to always try to allocate, or not allocate, but just set a pointer that you're not using to null. So for my example to work earlier, I need it to have been allocated. If I try to delete it twice, or delete it before it's even pointing to anything, then I'm going to get an issue. But here, if I just don't want it to point to anything, then the way I do that is with null. Now, similar to if something's already deleted, make sure you're not doing something like this, where you try to access null. This will give you a null pointer exception, or bad read access, depending on the system. It'll just tell you something similar. And that occurs because null is just a default value that points to nowhere in particular. And when you do this, you're trying to access things that just, there's nothing you're pointing to. So it can't get E if it doesn't know what you're talking about. In this case, this would also give you an error. So just use null as a placeholder. You'll see it's pretty useful. I have written assignment 5 and it's going to make you use it there. It's usually just as a placeholder if you don't think you're going to fill that space and you don't want to waste space, then you can put null. Any other questions on that? There's one last thing we'll talk about dynamic allocation, and then we'll get into an example of putting things together that we've learned over the past few weeks. Okay. One last thing as far as dynamic allocation goes. We have the ability to allocate variables on their own. It would also be helpful to be able to allocate arrays. So far with the 135 approach, we kind of have an issue because the way we've taught how to do that is you have some kind of constant usually, or magic number if you're, feeling like doing that, that says how big the array is. So let's say I'm going to do 100. And then you go into your code and you say, okay, I want my array now. It's going to be an array of example class things. And I don't know, I'll just call it E. And then you have to give a number here, right? The compiler sometimes lets you put a variable here, which is bad to some extent. But you're generally supposed to put constants here, or expressions that simplify down to some sort of compile time constant. But just, something that the compiler can figure out what the number is before the program starts, generally. And then it will go and allocate all that space. So, again, we haven't been considering memory in 135, but this just does go into space, and it says, all right, you want an array with 100 things, and so it'll go and say, all this memory space with these 100 things, that's my memory space for this array, let me do stuff with it now. But this was kind of a bad approach for two reasons. One is if we think it's too small, and one is if we think it's too big. We could have two possible issues with this. First off, if I have an array that needs to fit 300 things into this, then this isn't going to work. I'm going to lose 200 things, and the only way I could fix this is if I somehow know in advance what it is that I'm planning on storing in this and like how many things there are going to be in it. So it's generally a bad approach to actually do this kind of array allocation because of the fact that you rarely know exactly how many things you want in advance. So if I have too many things, I'm not going to be able to fit them all in, but if I only, let's just say, have 2 things in the array and it goes here and here, then I'm wasting 98 spaces. Which is also kind of bad because that's just all memory that we could be using for other variables, and we, again, run into the same kind of error or issue that we had earlier with memory leak, where now we just have completely unused memory space for the whole duration of the program, or at least until this array goes out of scope. And now we can't access it, we can't allocate variables there, we might get slowdown because we have to ask the operating system for more memory, and it slows down other programs, and so on. So static arrays are not good unless you know exactly what you're doing in advance. They are actually a little bit more efficient because the compiler handles them if you do know how much space you need in advance, but that's very rarely the case. So instead, let's go ahead and figure out a way to allocate this while we're running, rather than just at the program launch, or kind of be able to resize this array. The way we can do that is just with pointers. So I'm going to make an integer array here. I'm going to do it with an int pointer. And the way we're going to do this is we're going to keep track of pointers that point to array space. So I'm going to create one here just called R. And the way I allocate a new array is I do R equals, the new keyword comes back, and then whatever the type is of the thing that you want to allocate, and then brackets, and then the size. So here, let's just say 4. Roll off a little bit. And what this does is it goes into memory space, and once it hits this line, it's going to allocate 4 cells for our array. This will go and say, okay, well, I'm just going to put your array here. Let's just say here. Again, I should probably pick a better color. We'll say blue and put that there. And now we have a pointer to array space, and it will just allocate 16 bytes in this case, because it's going to be 4 groups of 4 integers, which are each 4 bytes. 4 groups of 4 bytes for an integer is what I meant to say. And so I'm just going to do 1 cell as an integer here. And so this is now position 0 is at the top of the array, position 1, position 2, position 3 are the memory cells in memory here. Now, the first time I allocate it, it's really just almost the same as a static array because I'm stuck here on a fixed size. But if I find out later that I need more space, I can always go get it. I could always delete this previous array and then make a new one. If I decide, well, okay, 4 is not big enough, I have the option to go and allocate more. And it probably goes somewhere else in memory. Let's just say here this time, and then allocates 6 things. So now there's, 1, 2, 3, 4, 5, and 6. This allows us to keep track of, or resize our space so that it's just how big whatever we're keeping track of needs. Which is why you'll commonly see in like files, it'll tell you how many things you're about to read. That way you can know exactly the array size that you're going to allocate, and then you can just put it in there and you have exactly enough space to fit everything in without wasting any or throwing things out that you don't need. One mistake I made here, if you're deleting an array, you actually need to put these in front of your delete. And then it will delete the whole memory space that belongs to. And again, I'm going to delete it because I don't want a memory leak if I'm going to allocate new space. And we have a question, could you get the pointer to traverse the array, or do you need to, oh yes, do you need a separate pointer? So you can use it, and it's actually exactly the same way you would use a normal array. So if I did R0, that would grab that here. So you can index it exactly the same way you do a normal array after you have the pointer. So R0 would be this one here, and if I did like R1, then it would be that guy. And you can actually traverse it using the pointer arithmetic we talked about in the last lecture as well. So because these are pointers, you can do a bunch of weird stuff with it. I could always do, this would actually be the same as that. This is a weird way to do it, and keep this in mind because this is an error that I see a lot of students make, is they will try to dereference an array, and because of the way that we say pointers work, where it always points to the top, if you do this and don't put an index, the top is the 0th element, and so this just gets the 0th element, and it's not obvious that that's the case, I don't think, by looking at it. And I've seen a lot of students get stuck for like a few hours just wondering, why is it printing only the first object? I'm dereferencing this correctly, but they're using the top of the array. So index it like normal if you can. Be very careful about putting stars in front of it, even though it is a pointer. You can do stuff like this. So if I wanted to access the second element, let's just say, like this, so this is the way I would normally say it, it's also valid to do it this way, R+2. will also get you to the same place, because that will do, so we said pointer arithmetic goes forward that many things. Because this is a pointer to integers, it's going to skip forward 2 integers worth of space, which is 8 bytes, and it will end up down here. So it's going to do 1 hop, second hop, and then it's now pointing to this one, which is position 2. And then I dereference it with a star. So these effectively do the same thing, but I would almost never really write it the second way, even though you totally can. I think that's not a good way to do it. Because we're doing this with pointers as well, it's also very important that you keep track of the count of the array so that you don't go out of bounds, because we totally could accidentally access like a 6th variable that's out here, and because this is just a pointer to the top and there's a bunch of space after it, if you accidentally go into position 6, let's just say, or anything past that, you're spilling into memory that's not actually part of your array, and sometimes it'll stop you, sometimes it won't. This is how a lot of vulnerabilities in security happen, is that you have access to this pointer and you can actually go beyond that and start writing things. It's how a lot of bugs in like old video games happen, or how like operating systems, people will like hack into it, and so they'll just start writing things beyond the scope of the array, or they'll somehow change the pointer to be in your operating system memory or something like that. So yeah, be careful about where you're going with these pointers as well. You don't want to go someplace that's outside of what it is that's actually yours. Usually the system will stop you, but sometimes it won't, and then you can get really weird things. For the sake of our programs, it'll probably just end up you print garbage, and then it'll just make it hard to debug your program. But it can lead to serious things. Was there anything else that had to do with these? Oh yeah, I was just going to do a quick example. Let's say I was to allocate an array. And pointer. Actually, let's just write a whole class. What we're going to do is we're going to do a simple implementation of the vector class. It's probably not how it actually does it, but I'm just going to write it this way. We know that the vector class, if you've used it in the past, it just allocates space as it needs it and tells you like the size of the thing. And so it's really been doing this dynamic allocation the whole time, which is why it's good and been recommended instead of using arrays if you know how to use them. So let's go ahead and just learn how to do our own. Let's actually do this in the code. I'm not going to write all this out. It's probably easier if we do it in Visual Studio. So let's write something that allocates space as we need it, and then allocates more as we run out of space. I'm just going to do it for a simple integer class, I think, and not go beyond that. I thought I had a header file for this. Am I wrong? I just wrote an example class up here. Let's write a new header file that's for an array of things, or a vector. We'll just call it like our own custom vector. I'm going to call it list. C++ calls these vectors for some reason, which I still don't really like. Most languages will call it a list, so I'm just going to call it a list here. That way we can differentiate it as well. So we'll just do it using namespace standard, and then I'm going to include this here. Okay. So I'm going to write a class. I'm just going to call it list, we said. And we'll just have it hold ints for the sake of simplicity. We could write it in such a way that it's like the vector where you can pick what it holds, but that requires us to know a little bit more that we'll get into at some point. Okay, so first things first, we need an integer pointer, which is going to be our pointer to our array that we just discussed. I'm going to call this R. And then we're going to need two other things. So first off, we're going to need to keep track of an int for how many things are inside of it. I'm going to call that the count. We'll expand upon that further later. And then we'll start writing some public functions. Okay. So we need a constructor first off. We'll make a constructor that takes the initial count, we'll say. So how many things we want to store in it by default. And we'll just do that with the new operator. I'm going to space this out so that it's a little easier to read. We'll say R is equal to new int initial count. And then let's just store that count variable as well. And then we'll write our own kind of like pushback function. I'm just going to call it add because that's what most other languages call it instead of pushback. So I'm just going to call it add, and it will add an integer. We'll say n, adds the integer n to the end of the list. Now we know that the size, I need to actually put a type void. We know that the size of the array is just going to be this, so we'll need to always allocate more space whenever we put something in. So for our example here, if I was to, let's just say, have an array that's already 3 long, let's just say, and has some random numbers in it, and then I was to call the add function and wanted to add 8 to the end of this, I have no room to put it at the end here, because this is just like garbage space. It belongs to something else. So I need to allocate more space and then put it at the end of the array. So if this is 3 already, at this point the count is 3, and the array pointer is there. What I need to do when I add 8 is I need to make the array longer, so I need to allocate some new space, make the array point here, get rid of this old one that points to the old one, delete this before I do that, and then update this count so that it's 4 and I know how many things fit into it, and then put the stuff in there. So make sure I have the 0, the 4, and the 7, and then add the 8 to the end. I didn't do that in the best order, but the idea is that we need to make a bigger thing, copy everything over, add the thing to the end, and then update all of our class variables. The order I need to do it is I need to copy it before I delete this, right? Because otherwise I lose it. So let's do it in that order. Let's actually try to write the code for this. And for implementation, you should probably never do it this way, but I'm just going to do it anyways. And for the sake of assignments, it's okay to do it this way as well. Although, real life, please don't ever do it the way I'm about to do it. So first things first, let us go ahead and make the new array. So I'm going to create an integer pointer. I need another pointer to the new array I'm allocating, which means I need to keep 2 pointers at the same time. Just for the same reason you use a temp variable and something like bubble sort, anything where you swap, you don't want to lose access to the old thing while you're kind of swapping things over. So I'm going to make a new thing. I'm going to allocate it to be count plus 1, let's just say. So I'm going to allocate it to be 1 bigger. And then I need to copy everything over. So let's comment all of this. Allocate the new array. Copy everything over. So we'll just do a for loop. I equals 0, I less than the count tells us how many things there are. I might want to rename this to be size. It's before this bites me later. I'm going to rename this to be size really quick. Or do I? No, I think this will be fine. We'll see. I think I made this mistake last time I taught this class, and my variable names ended up being backwards because I did this example weird. Hopefully it works out this time. We'll find out. Anyways, I need to copy everything over, so I need to copy from my existing array, which is this member. It's called R. I need to go and copy into the temp position. So temp sub I becomes the array sub I. And then add the new element to the end. The new element is going to go with the count position because the count position represents the next one. So consider here that this would be position 0, 1, and 2, and here, where'd my pen go? This would be 0, 1, 2, and 3. Position 0, 1, 2, and 3. And so the count before I actually added this over was still 3, because that's how many things were in the array beforehand. So notice that the index always tells you how many things come before it. So here at this position, 0 things come before the 0th position, 1 thing comes before the first position, 2 things come before the second position. So I can kind of just use the index of the count to put things in the correct location. Because I know that there were 3 things already in the array, I'm just going to put this at the 3rd position. So I'm going to say temp sub count equals the integer that I'm adding to this. Note that there are also a bunch of different orders and ways that you can do this in. This is just one way to do it. So that's in there now. We've copied everything over, and we've added the thing to the end. Now we need to deallocate the old array because we don't want it to just sit there. And we also need the array variable to point to our new one. So we need to deallocate the old array and update our pointer. So I will delete the old array that's being pointed to. Deallocates all that space. So this effectively here did this. It gets rid of the 0, 4, and 7 that existed already. And then we need to update our array pointer so that it points to the new array that we've created, which is the temp pointer that we had. And then last thing, we'll just increment our count. And that should be everything. Really quick, let's just write one last function here called print items that just prints everything so that we can verify that this works. And we'll just see out r sub I, and then we'll throw in a space, I guess. That's probably fine. And then I'll put an end line at the end. Okay, so just to verify that this works, let's go to our main really quick. Example of using a dynamically allocated, I would say, collection variable. I'm going to create a list. We'll just call it list. And then I will start it. I should probably make a default constructor as well. Let me make a default constructor. This is also probably good for practice as well. So if I did a default constructor where it had nothing inside the array, then obviously my count would be 0. And then if I allocated nothing yet, then this would be an example where using null would make sense. I'm going to set this equal to null just to mean that, well, there's no array because it contains nothing. In that case, I should also check here and do something. So I think this really kind of works out fine with the way I have it, except for the delete r part. So if r does not equal null, that should be the only issue that I have. If it is null, then all of this is going to get skipped because the count is 0. It'll make a new array of size 1 because it'll be 0 plus 1. It will put the thing at the correct position, which is position 0, the only thing in the array. And then here, this will only delete the old array if it exists, meaning it's not null. So the way I did this, I think, is actually pretty nice because it's just one line. But be careful. There's a lot of different ways that you can do this. I think this is kind of a simple way to do it. Just make sure you're not deallocating anything that is null, and that you're not like copying over things that are null, or doing anything weird like that. I think this is probably all right. Yeah, so I'm just going to do that. I think we already finished the default constructor. We'll say that's probably good enough. This makes a new list, and then I'm just going to add some items for the sake of our example. So I'll add 4 and 7, and then let's print it. And then we'll also add 6, let's just say, and then we'll print it one more time. Let's just verify that this works. And we run it. These destructors are getting called, and we see that it first prints 4 and 7 on this line because I added 4 and 7, and then I looked at the contents of it, and then I added 6 and printed it again, and we see that now 6 is at the end of it. Cool. So we have an array that's able to resize itself as needed, which incurs a little bit of extra time whenever we do some allocation, which we can kind of get around. We'll see with some of the data types we use later, but is pretty good on space. It never uses more space than it needs to. So we kind of have addressed that issue if it ever shows up. Cool. We have that. Let's talk about ways to improve this that are just kind of easier to do. Now, the main issue with the way I've implemented it, and the reason I would say to never do it this way, is because it needs to resize every single time you add something to the end of it. And there's different ways you could go about trying to fix that, but you want to avoid doing allocations as often as possible. So every time I add something, it needs to recopy everything over from the old array and then also make the new space, and that takes quite a bit of time. So, sorry, 1 second. Sorry about that. Right, so we have like this memory issue where we allocate things pretty frequently. That's a bit of a problem. So one way to avoid this would be to just allocate more space every time, so we don't have to allocate as often. So what we might do is allocate, instead of just the 1 extra cell, we might allocate, let's just say, 3 extra spaces, and that way, every time we add, we don't just have to, allocate new space every single time. We maybe just have to do it every 3. That's one possible approach. Another possible approach would be to allocate an array of pointers and then just have them point to any sort of new space that we allocate. That would be fine. But let's try doing this implementation really quick and modify the code we have right now just to make that work. We'll add a few things. I'm going to add a size variable. This will represent how many things have actually been allocated, and then we'll use the count to represent how many things are inside of the array. And then we'll need one other variable, which we'll just call the constant. We'll just say allocate size, being how many things we want to allocate on top of the array every time that we need to allocate. I have an error here. Did I make a typo? Provides no initializer for... Oh, I need to finish writing the const part. Let's just say 4. Normally I would say you want to make this a little bit bigger, but that's okay. So here, we need to change a few things, specifically in add. We want to allocate a new array, but we don't need to do this every single time now, because we said we're not just adding one thing to the end of it every single time. and so we only want to allocate it if we're ever out of space. The way we can do that is we can check if we're out of space by checking the count and the size variable that we have. First things first, I think we should allocate this. I'm probably going to make this size now. We'll call this initial size. Like that there. We'll make the count equal to 0, and then we'll initialize the size to there. Okay, so this will allocate some amount of space, and then we want to check if the count is the count plus 1, let's just say, is going to be greater than or equal to the size. Really, we only need to check if it's equal to. Then that's when we need to do the new allocation. So now we'll only allocate when we're out of space, which means we'll copy some of this over. Now we're going to allocate more than one space every single time. And then I need to move all this stuff over as well. I'm going to change this. So copy everything over. We'll still do that. And then I will deallocate the array if necessary. So really all of the code that comes to allocation and deallocation will now go into our if statement, because this is only if we're out of space. We will create a new array, we'll copy everything over, we'll deallocate the old one, and then we'll make the current array pointer point to the new one. And then regardless of whether we allocate an array or not, we always need to add the thing to the end, so I'm going to do it this way. And then we should always make the count bigger. I'm missing one extra thing, which is that the size should also get bigger. So size plus equals, what do we call it? Allocate size? Cool. So now we've effectively, we're only allocating when we run out of space, and then we do all the same stuff that we did before, and then we also keep track of our new size variable that just represents how much space do we have. Here in this, just so we can see it, the count would still be 4, and the size in this example would be 6. We're using the size to represent how much space we have, and the count to represent how much of that space we've filled, which is similar to how you may have used a static array in the past. Let's just verify this works really quick, and then I think that about does that for dynamic allocation. Do we see it? So, oh yeah, sorry, there it is. So it's 4.7 and then 4.7.6. So see, it still seems to print correctly. We could maybe check the size and the count as well if we really wanted to. Oops. Let's go back to this add function really quick and just take a look at it. For the sake of our example, let's add a few more things to this as well. So let's add 8, and then let's add 27. Actually, let's throw 2 breakpoints, one here and here, rather than just on the add function. Up to this point, it should just add everything normally, because the allocation space that we've given here is that it allocates 4 things at a time. We should see that it will only allocate once we get to this last call here. We'll run it first. See it run, it gets to the add 7 part, so it's going to add the second thing here. We go to it, and the count is currently 1 because there's only one thing, being the 4 in this array. It might be a little bit hard to see the debugger, but you can see here that the R contains 4 things, and the first item is a 4. The count is 1, and the size is 4. Apologize if it's a little too small, but this seems to line up with what we were saying. So it allocated 4 spaces, filled the first one. If we continue into our program, by the time we add this 27, then it should have 4 things already in it. So we'll see that the count is 4, because we've added 4 things to it. And the size is 8. So I must be allocating a little early. I think I don't need this +1. Sorry, let's rerun that really quick. It is still gonna work, it's just gonna do the allocation one before it needs to. Which I guess we don't really need to do. Now we go to add a 27, I think it should be okay now. So we see the count and the size are the same, because we've added 4 things, and the space it occupies is 4 things, and it's going to go and do the allocation code now only. So these matched. It'll allocate all this stuff. It's going to go into some of the other C++ libraries. But by the time we get down here, we should see that the count is still 4, because there's 4 things in the array, and the size is now 8, so it has reallocated everything. And by the end of it, it still prints everything fine. It doesn't look too flashy when you just look at like the output, but it only allocates things when it needs to now, which is really good, and we've kind of stopped it from allocating as often. We still might have a little bit of wasted space this way, just consider, because I am always like giving some extra space here and not necessarily filling it until I need it, and maybe I don't need it, but it's generally going to be like a lot less space than if we just made one big array allocation. So any last questions on that at all? And I will update the code on Canvas as well so that this goes up. Okay. One more thing we'll talk about. I don't think we have enough time to talk about the next subject yet. I think that'll take too much time. But I did want to talk a little bit about RNG, just because I saw the question a lot on Discord, and I wanted to clarify some things about how RNG works. First things first, we should probably say you can't really make things random in reality. You can make things seem random, but true randomness is not really possible. So if I want to generate a number, it may seem random, and whatever events it leads to may seem random, but there's some sort of underlying thing that just determines it. So the common way to make something seem random is to just generate it in such a way that's difficult to explain, so that the person who is seeing the random number generation thinks it's random. So they kind of like perceive it as random, or they just don't comprehend how those numbers are being generated. In that case, you can say your RNG is kind of like good enough, because if it's unpredictable, then it is close enough to seeming like random from the user's point of view that it might as well be random. But realistically, these need to generate numbers in some way. So you might just have it generate from a pool for one thing, and just pick 0 first, and then 4, and then 7, and then 8, and then kind of like wrap around and maybe span all the possible numbers that you could do. Would be one approach. Or another approach is to use variables in the environment that the computer's in that seem unpredictable to the user, so that it again seems random. So things that you usually use for that would be time, or temperature of maybe the CPU, or if you have like some sort of thing that measures temperature in the environment, or humidity, or something like that. If you're running on like a game, you might factor in frames or user inputs. You might just add a random number, like every time the user presses B on a controller, or like A on the controller, you might add by a different number. But you want to do something that seems kind of unpredictable, and may rely on something that feels unpredictable. So time is kind of unpredictable in that if you were to measure based off of like the clock on a computer, it goes so fast that because it's like measuring in something like milliseconds that the user might not be able to notice anything. So you see that's why a lot of the time we have srand time, where that will get the system time, and that's how it sees things. But the point being, you probably want something that the user is not going to be able to predict on their own. Now, the other thing was seeding, because I think this is the question I got most often on Discord. It's like, why is my output always the same? And so because these algorithms are deterministic, they always have to work in some sort of way, then they're usually dependent on a seed. So the specific random function in most languages gives you the feature to seed it. So for my example, let's just say I have a random number generator that's really bad and it just goes in order 0, 1, 2, 3, ... 2 to the 32nd -1, assuming it's a uint -1. It does all these numbers and spans the whole thing, but it just doesn't order. It's really bad RNG, but it's uniformly distributed in that it's going to generate each number once, and it's going to cover every possible number. Let's just say that's positive. Now, if I was to just do this normally and get some random numbers, the way you normally do that is with the rand function, then the first thing it's going to return is 0, and then it might return 1 after that, and then if I call it again, it'll return 2, and so every time I call this random number generator, it's going to follow some sort of pattern that I've dictated, or it's going to have a way to generate the next number. In this case, the way that I'm generating the next number is just adding 1 to the previous number that was generated. Realistically, it's probably going to be a lot more complicated, so that it's more unpredictable, but this is just kind of our simple example. Because this is the way that my program works, and this is the way that really any of these are going to work, where they have to have some sort of way to generate the next number. In this case, I'm just adding 1. So this adds 1. That's my method for generating things. Then if I run this program every single time, the first random number is always going to be 0, the second random number is always going to be 1, and the third random number is always going to be 2. In order to avoid this, most random libraries, and C++ is no exception, give you the ability to seed, which just tells you something about the starting value. Not necessarily the starting value itself, like the next thing it's going to generate, but something that determines how it generates the first number in general. So here, maybe the way I have it seed is it always just starts that as the first number. So now if I was to seed this as 4, the first number will be 4, and then this will be 5, and then this will be 6. Because of that, you'll get patterns that are exactly the same way every single time if you use a common seed. That's why in assignment 2, because that's where I'm seeing most of the questions, you're going to see the dice roll is the same every single time because it's seeded consistently. Even though it's doing random number generation, randomness is not real. It's more of just like a concept, right? It's not physical, or as far as we know, right? The universe is deterministic. Everything behaves in a way that makes sense within the laws of physics and all that. So these are going to follow a specific pattern if you always seed it the same way. So that's why in assignment 2, you're always going to see the same dice rolls every single time. The way you do that unpredictability is by seeding it off these factors that are unpredictable, like time and temperature and that stuff. So just that hopefully answers everybody's question about assignment 2, why you're getting the same numbers every time. You should be getting the same numbers every time because it's seeded exactly that way. And you'll see, for the sake of our classes, that's going to be kind of there because you don't want to make the TAs suffer and have to deal with random number generation and reading through your whole program. But consider that if you're ever writing an actual program, that your randomness isn't going to come from the algorithm, because the algorithm is deterministic. It picks things in a fixed way. It has like certain rules on how it picks the next number. In my case, it was just adding 1, but it might be like taking powers or doing other stuff. So your seeding is really going to affect everything. So that's why you seed it based off of these. So just keep in mind that srand in C++ is generally how you get your numbers, unless you write your own RNG function. Any questions on that? I just saw that question like 4 or 5 times this weekend and thought it would be good to address. Especially because we only had like a few minutes left. Okay, I guess it is 6:45. If anybody has any other questions, I'm going to stick around a little bit. But if not, remember assignment 3 is now due tomorrow, and then assignment 2 is now due tomorrow. Sorry, don't want to make you panic. And then assignment 3 is due next week. So just try to get that in. And yeah, I'll see you guys on Thursday.